In the previous unit, it has been shown that all Q values depend only on CS, when we design the nutrient supply such that substrate is limiting and all other nutrients are in excess. Also, all Q values are flux coupled to each other, which makes QP, mu and other Q rates only dependent on CS under these substrate limited conditions. This is the basis of black box models. Also, we already mentioned two product classes. When the synthesis of product costs energy, the process must be aerobic because substrate needs to be oxidized with oxygen, which will supply energy for the product reaction. However, when the product makes energy, an anaerobic process is possible because oxidation of substrate is not needed anymore, so we don't need oxygen. Now we will have a better look at these two product classes from the point of view of setting up a black box model. For both product classes, substrate is taken up by a transporter, following a hyperbolic function in CS as discussed in the previous unit. This function has two parameters, Qs max and Ks, and both parameters are assumed to be constant for a given organism substrate combination, but also at a defined temperature and pH. However, when you are working with an energy consuming or energy producing product, both follow the same kinetic format for substrate uptake, which is the hyperbole. All microorganisms have to maintain their structure integrity against constant leakage of molecules over membranes and degradation of cellular polymers. Now, to counteract these degrading processes like pumping out of leaked molecules, repair of degraded molecules, the cells must spend energy at a continuous rate, which requires substrate catabolism at a maintenance rate Ms. This already shows that part of the substrate which is taken up is used for maintenance. Also important is to realize that aerobic Ms values are about a factor 10 lower than anaerobic Ms values because the energy produced per mole glucose is aerobically roughly 10-fold higher than anaerobically. Now, having discussed the common aspects, hyperbolic substrate uptake and maintenance, we must now engage in the differences for the two product classes. Let us first discuss the energy consuming products such as occurs in the current PDO process. The substrate which is taken up is distributed over three network processes. Formation of biomass, which occurs with the rate mu, and with the consumption of a mole substrate per mole produced biomass, leading to a partial substrate consumption rate for growth equal to A multiplied by mu. Formation of product with rate Qp and consumption of B mole substrate for each mole produced product, which leads to a partial substrate consumption rate for a product equal to B multiplied by Qp. And finally, maintenance with a partial substrate consumption rate Ms. Now please note that each of these three processes requires energy, making the aerobic conditions necessary. We can now put our insight of these three reactions into one equation where we can trace back where our substrate is going to as shown in the image. This is the Hubbard-Pert substrate distribution relation with three terms which represent the partial consumption rates of substrate for growth, A multiplied by mu, for product, B multiplied by Qp, and for maintenance with the rate Ms. Moreover, the cell has a branch point, as indicated, where substrate goes either to biomass or to product. Now, we call this situation kinetic coupling, where Qp and mu are coupled to each other in characteristically a non-linear way, as shown below. Now, let us now construct a black box aerobic model for PDO. The glucose uptake rate, Qs, is a hyperbolic relation in CS, as shown. The Hubbard-Pert relation, with its three terms, is also given, And finally, we have a nonlinear QP-mu relation, which shows that QP increases with mu in a nonlinear fashion. By combining these equations, you can see that we have 3 equations and 4 variables, which are Cs, Qs, Qp, and mu. And therefore, we have one free variable, which can be Cs, which is not surprising because we work under substrate limiting conditions. Another practical choice for the free variable is mu, because we can manipulate this in a chemostat as shown last week. And also in designing processes, using mu as a free variable is practical, is convenient. Now, from an economic point of view, now we can go into some calculations. And especially the ratio Qs over Qp in mole substrate per mole glucose is relevant, because it relates essentially to the variable cost of your product, of your process. So it gives you the mole glucose consumed for each mole PDO produced. Now, the Herbert-Pert substrate distribution relation gives you Qs, and the Qp-mu relation we can use. And we can combine this in the relation to calculate Qs over Qp as shown in this screen. After some algebra, we come to the conclusion that Qs over Qp, look at the lower equation, only depends on mu, which is the free variable, by the way. Now we can translate the algebra in graphs, and the graph shows you that there is an optimal growth rate where the consumed glucose per mole PDO is lowest. And you can do that mathematically, and calculation shows that this optimal growth rate is, this occurs at an optimal growth rate of 0.0245 hour minus 1. And of course, at this optimal mu value, you can calculate also the optimal Qp value using your Qp-mu relation. And you can calculate the optimal substrate consumption uptake by using the mu optimal and the Qp optimal with the Herbert-Pert relation. And so in the end, we find the Qs optimal value and the Qp optimal value, which tell us that if we take them both, that we consume 1.29 mole glucose per mole PDO. Now it's very relevant to compare that number with the parameter in the Herbert-Pert equation of 0.8 mole glucose per mole PDO. Our optimal value is obviously higher, 1.29 versus 0.8, but this is of course due to the fact that we also have not only product formation but also growth and maintenance. Now, by using the Herbert-Pert relation, we can get some insight in how the glucose is used for product formation, growth, and maintenance. So we have the Herbert-Pert relation, we have the mu optimal, we have the Qp optimal, we can calculate the Qs optimal, so we can enter all these values, and we can see that the Qs optimal is 0.0294, value of 0.0294. This is composed of 3 contributions, as indicated in the screen. The first part, 0.25 multiplied by the optimal growth rate. The second part is 0.8 multiplied by the Qp optimal and the maintenance term. And we can translate all these numbers in relative amounts, and we come to the conclusion that under the optimal growth rate, the glucose is 62% going into growth, 62% going into product formation, 21% into growth, 17% into maintenance. So at first glance, we seem to have a not too bad production organism. So that is what we can learn. Now, let us now consider the black box model for an energy producing product. For example, ethanol from glucose. The cell has now only 2 processes and not 3 as in the previous example. And these 2 processes are biomass formation and maintenance. In the biomass formation process, substrate is used with a mole substrate to make 1 mole biomass, leading to a partial substrate consumption rate A multiplied by mu. Maintenance has a partial substrate consumption rate MS. Both processes require energy, which is expressed by a stoichiometric coupling to the production of energy which is reflected in the production of ethanol in both processes. Now, this leads then to a Herbert-Pert relation of only two terms, telling you that substrate is used for growth and maintenance, and essentially also a linear QP-mu relation because of the stoichiometric coupling of growth and maintenance to ethanol formation, which is the product. Now, we can now summarize our insight in black box models for the two product categories, and we see that these are partially similar, like the substrate uptake and maintenance, but partially different, like the QP-mu relation, which can be nonlinear or linear, and the Herbert-Pert relation, which has three terms, or only two terms. Now, having proposed to you the structure of the black box model, next time we will focus on the parameterization of these black box models. So see you back next time.